So, I understand that the title of this school is, well, anyway, it contains the word concepts, and I was given to understand that I'm one of the concept people. So, anyway, I wanted to tell you a little bit about, let's say, a personal and parochial view of some aspects of the physics of correlated electron materials. As was said, my name is Andy Milllis. I'm from Columbia University. So, let's say the stereotypical theoretical physicist view of condensed matter physics I obtained from Zachary Fisk. In condensed matter physics, you start from the periodic table, and from that you derive a description of the long wavelength physics of materials, preferably described by a quantum field theory with a topological term. Anyway, what I want to do a little bit in these lectures is talk about where we are on decorating this periodic table a little bit, and saying what we understand about going from actual materials to actual behavior. This is a vast subject, and I will only be able to cover a little bit of it. But just to motivate what's going on, let me start with a material which has been famous for 25 years or something now, which is yttrium-1, barium-2, copper-3, oxygen-7. This is a somewhat complicated compound which has 4 elements which are put together in this particular crystal structure, which has a complicated set of units. Basically, you should think about it as having a plane with this structure of copper, oxygen, copper, oxygen, copper, oxygen, copper repeated. Then another plane which contains nothing but this yttrium atom. Then another plane with this copper, oxygen, copper structure. Then yet another plane with a barium atom and some oxygens. Yet another plane which has some missing intermediate oxygen, so it has copper, oxygen, copper chain. And then that whole structure repeats. So, very complicated structure. And of course, you all know that this thing was found to be a superconductor at temperatures which were remarkably high by the standards of the time. So this immediately raises the question, what is really special about this kind of compound? Now, over the years, our ability to address this question has been sharpened. Material scientists can do amazing things. One of the rapidly growing fields is what you would call, well, what I call oxide superlattices. One of the papers which really kicked off this field was by Otomo, Dave Muller, and Harold Wang, now 8 or so years ago when they were all at Bell Labs. What they showed was that you could grow atomic scale superlattices of compounds which have interesting electronic properties, and you could grow in some approximation essentially any superlattice you want. So this is a transmission electron microscope picture of one of the superlattices they made. The white things, the bright white things here are actually strontium ions. The less bright things, that's right. The less bright things are titanium, sorry, I got it backwards. The bright things are titanium ions, the less bright things are strontium ions. Oh, you know what? Now I understand why I'm confused. I mislabeled this. So what this is actually SRTiO3, LaTiO3. I apologize, this label is incorrect. All right, so the more bright things are lanthanum ions, the less bright things are strontium ions. So this is a case where you have strontium 1, 2, 3, 4, 5, lanthanum, strontium 1, 2, 3, 4, 5, lanthanum. And you can see that at least over the averaging done by the transmission electron microscopy, which averages over about 1,000 angstroms of the sample, you have an essentially perfect structure with atomic resolution. you can go on, and they show that within certain limits, you can make essentially any combination of this you want. Here you see pictures with thick white lines going down to thinner. This is 5 strontium, and then 5 lanthanum, and then a bunch of strontium, 4, 3, 2, 1, etc. All right? So things are getting to the point where you can artificially create a wide variety of things, at least in 2 dimensions, and one's ability to play games with dimensions is going down. So, many systems can be made, and many effects can now be produced. A striking recent report from the group in Cannes in France is that if you make an analogous superlattice out of lanthanum vanadate and strontium vanadate, that's the picture here where you have a strontium layer, a vanadium layer, lanthanum, etc. If you choose your superlattice correctly, then you can get this thing to be magnetic. Here is a magnetization versus field hysteresis curve. The black dots are taken at room temperature, and a person looking at this would normally conclude that this is a room temperature ferromagnet. Even though if you make a solid solution of the lanthanum and strontium vanadium, you get this red curve, which is either non-magnetic or much less magnetic. Right? So you could ask, for example, what is special about this superlattice and why does it have room temperature ferromagnetism? Another highly stimulating idea came from Gignac Paliulin. He said, well, all right, if you can make anything you want to out of these superlattices, why can't you make it a high temperature superconductor? All right? So here's the paper. What they said was take this material, lanthanum nickel oxide. All right? This is a cubic material with a relatively simple crystal structure, and it's in fact just a paramagnetic metal. And they said, well, if you play the right games with this, if you make a superlattice with a layer of lanthanum and nickel, and then a layer of some other metal, for example, aluminum oxide, and then you repeat that, you will get a 2-dimensional electronic structure. And if you fiddle this thing correctly, you will get this electronic structure to look sort of like that of the yttrium, barium, copper oxide superconductors. To be more specific, and I'm showing you these pictures because I'm going to want to come back to them at various later points in the lectures. If you just take this cubic material, what we're talking about is electrons which live in basically nickel d orbitals, and the d orbitals you care about in this compound are 2. There's a 3z squared minus r squared, whose wave function can be rendered like this if you like to render wave functions with Mathematica. Actually, I think this is the charge density associated with the wave function. And the other one is x squared minus y squared, which looks like this. All right, so these 2 orbitals, well, they are among the 5-fold degenerate d multiplied in free space. This material is in a solid. It doesn't have the full O3 rotation symmetry. The 5-fold d multiplied is broken down into a doublet and a triplet, and these 2 guys transform like a doublet. So in bulk cubic lanthanum nickelate, you have these 2 orbitals which are degenerate with each other, and if you now make this multi-layer structure like I sketched, you break the symmetry between these 2 orbitals. These characters argue that this orbital goes up in energy, so the result is an essentially planar array of x squared minus y squared orbitals, which is just the electronic structure, which is the essence of high temperature copper oxide superconductivity. And therefore they said, well, if you just make this oxide multilayer, you'll get a new family of high temperature superconductors. People have not yet really been able to do that, but it appears that as you get closer, it looks less and less likely that it's going to be a superconductor, although there's actually rather funny business about metal insulator transitions in that system. But it raises the question. All of the arguments in this paper are entirely qualitative, right? And based on a sort of botanical resemblance between one set of orbitals and another. So you may ask, how do you know this is right? Or what would you do, really, to establish if it's right? So, more generally, you might ask, if experimentalists can make anything, what would you want them to make? Or, to put it more formally, well, to put it more informally, I didn't quote this. When I described this field a few years ago to Stuart Parkin at IBM Almaden, he said, great, so tell me what I have to put together to make a high-temperature superconductor. So this is perhaps the more formal way of posing that question. All right, now, why is this a hard thing to do? Here, I'm just going to repeat some elementary ideas which I believe have been discussed in this school in previous years. But you might think, that this just shouldn't be that big of a deal. We know what is the Hamiltonian. We have some number of electrons. They have a kinetic energy. They feel a potential which is provided by the ions. They interact with each other. So we know what is the Hamiltonian. We know what to do with the Hamiltonian. We write down a Schrodinger equation. And so why don't we just stop complaining and solve it, and then just find out the answers for each structure? All right. So the answers, as you know, are that this problem is essentially computationally impossible. One way to look at this is to say, if you take, for example, one of these transition metal oxide materials, a typical lattice constant in the material is, say, 4 angstroms. An interesting length scale might be 100 angstroms, 200 angstroms, something not much smaller than that. So if you want to say anything intelligent about the behavior of this material, you will discover rapidly that I don't know how to multiply 100 by, raise 100 to the power of 3. There are a few zeros that got lost here. But if you have on the order of 1 electron per unit cell and you have a volume of 100 angstroms cubed, that's 10 to the 6 electrons. If you want to think it's two-dimensional, that's still 10 to the 4. So apart from the few missing zeros here, that's a lot of degrees of freedom in your Schrodinger equation. And furthermore, because the electrons interact, all of the coordinates in your wave function are, of course, entangled. And therefore, the resulting differential equation is essentially impossible to solve. What makes it worse, as again I understand has been discussed in this school, is that of course we're talking about fermions. A fermionic wave function has to be a completely anti-symmetric function of the particle spins and coordinates. And imposing that constraint of anti-symmetry in any calculation one might want to do directly is essentially impossible. All right. So, therefore, if you're going to talk about these things, you need some other approach than a direct brute force attack on the Schrodinger equation. Right? Now, the thing which is widely used for many materials is density functional band theory. And I felt that it was important to discuss that briefly for 2 reasons. First, it is actually the main tool that people use to understand properties of wide varieties of materials. And second, it introduces an idea which I think is conceptually very important, right? And the basic idea is that you don't solve the problem directly. Instead, you use the solution of an auxiliary problem, which is much simpler than the direct problem you want to understand, in order to obtain a limited, but still you would hope useful class of information about the problem which is of interest. Okay. So, and I should say, by the way, please stop me at any point to ask questions. One of the bad things about PowerPoint talks is that somehow it sort of discourages questions. On the other hand, the good thing about it is that you don't have to look at my terrible handwriting. Okay, so density functional theory. I mean, it has a long history, but the first key paper was the one by Hohenberg and Cohn, which is written here. And what they did was they proved a basic elementary theorem, right? And this theorem says that there exists a functional, phi, of the electron density for a given quantum mechanical problem of electrons, which is such that this functional is minimized at the correct physical ground state density for any problem, and its value at the minimum gives the ground state energy, right? And when you think about it, that's sort of remarkable. You normally think about quantum mechanics as involving a wave function with all the coordinates of all the electrons and phases inside the wave function and all that stuff. And what they're saying is that in some sense, you don't need to know all that. All you need to know is a classically defined variable, namely the density, and you're in business, right? Even more remarkable, they say that the functional is a sum of 2 terms. One term is just the potential energy that the electrons in this case feel due to the lattice. That I wrote here. This is just the classical potential energy. The other term is a functional, which is universal in the sense that the only thing it depends on is what is the interaction between electrons, in this case E squared over R. It doesn't depend on the and on the form of the kinetic energy, in this case p squared over 2m. It doesn't depend on the lattice. All right? So therefore, the only material dependence is in here. This is just some known function which is the same for everything, and therefore all you have to do is get this function, put in the potential corresponding to your favorite lattice, and minimize. Yeah?
Can you elaborate on this a little bit? Always, in some ways, it's remarkable. In some ways, it's kind of obvious almost, because for the quantum field theory, you have the compute effective action with a function of some external field.
Correct.
So this is very much like it.
This is very much like it, and I'll point you. I'm not actually going to use that approach, but I'll point you to a little later. We'll point to. Actually, it might not come until the third lecture, but I'll point to references which develop this precisely from that point of view.
I mean, it seems like there's just a Legendre transform.
This is, in a strong sense, just a Legendre transform. And if you like, you could write down, I mean, again, I'm not going to go into details. There's a RevMod Phys by Kotliar and others, which, as I say, I will, from 2006, whose reference I will give you. But basically, in some very simple formal sense, if you just write down a partition function as some kind of fermionic path integral, all right? And now you make a Legendre transform, so you just perform this integral, so you define a sort of z prime of n of r with an appropriate functional constraint. Then you can generate this universal functional. It's essentially that kind of thing.
I had a funny story where I was having tea with Walter Cohen about 15 years ago, and I was trying to describe this point of view, and he told me that I didn't know anything about density functional things. Fair enough, but it's a very different language.
Yeah.
So
correct. Yes. That's true. In fact, both of those statements could be true. This is elaborated in detail in the Kotliar and Sabrasov review article, and also in a nice article which only seems to exist on the archive by Antoine George. Okay, but from a practical point of view, all right, if you can make this work, it's incredibly useful because you have a machine and you want to do any different material, you just stick different things in here. All right. Now, because the proof is elementary, I thought it's worth giving a proof which doesn't involve functionals or anything, and this is essentially what's in this article. All right? And it's another way how to think about this. Look, if you just take your Hamiltonian, it's clear that the ground state energy is a functional of this potential. And the reason is that, after all, you just solve the Schrodinger equation with that potential and that gives you an energy. So the process, although you cannot do it in practice for the reasons we discussed, of solving the Schrodinger equation at a given potential gives you a mapping from the potential to the energy. And you will also observe that the energy is just the expectation value of the ground state wave function, and it has two terms. Here, the external potential just couples to the particle density. That's the thing we had before. The other thing is the expectation value of the kinetic energy and interacting parts in the ground state wave function. Right? So second, I hope this faint green is actually visible. Not only is the ground state energy a functional of the external potential, the density is a functional for exactly the same reason. You get the potential, you get the wave function. From the wave function, you can get the density. Fine. So far, so trivial. All right. Then, the key statement is that this external potential, that this mapping can go the other way, that the external potential is, up to a constant, because energies are always uncertain up to an additive constant, a unique functional of the particle density. All right? And what they said was, what they did was they presented a proof by contradiction. They said, well, let's suppose that this were not true. All right? So that there are two potentials, V1 and V2, which are different, and not in a trivial way, which give you the same density. All right? Then you can derive a contradiction in a very elementary way. All right? If we have two potentials, we have two Hamiltonians, we have two energies, we have two wave functions, ground state energies. So the ground state energy, if I choose potential 1, I'm going to call E1. It's the expectation value of H1, which is the Hamiltonian with potential V1, using the ground state wave function. Right? Now we know, because the ground state energy is the lowest energy, that if V2 is a different potential, it will give a different wave function. So if I take the expectation value of Hamiltonian 1 in the different wave function, I have to get a bigger energy. All right? But the only difference between these two Hamiltonians is in the potential. So therefore, I can take H1 and convert it into H2 by adding and subtracting the correct potentials. So therefore, I could say that E1 is less than this expectation value, which is E2, what I would get if I put H2 here, plus the part which depends on the difference between V1 and V2. Right? But there's nothing special about 1 and 2, so I could just rerun the same argument with 1 and 2 interchanged, so I get these two inequalities. Right? So therefore, if I add these two things, then I conclude that E1 plus E2 is less than E2 plus E1. Yes?
This assumes that you have a unique ground state.
Correct. Yes.
What if you don't? Or you have gapless.
Right, so basically the way it works is you make a limiting process. What you have to do is basically ensure that your Hamiltonian is unique. So there are two cases. If you have a rotation, some kind of symmetry, right, then basically what you do is you put a term that breaks the symmetry. So you imagine putting your system in a finite box of some sort and adding a term which breaks whatever symmetry it is, which gives you your gapless degree of freedom. Right? And then this is true in the limit as that symmetry breaking term goes to 0.
But you have a metallic ground state.
If it's in a finite box, then it's not. Right? So then you have to take the limit, then this statement is true, and the limit as the box goes to infinity. Yes. So my understanding is that this is a case which has actually attracted the attention of a lot of mathematicians, and their belief is that that limiting process works. So then you can go on to show that this ground state energy is therefore a unique functional density, and therefore that, and you can go on to show therefore that this functional is minimized at the density which corresponds to the potential which you put in. Right. So therefore, as I said, to get the energy, all you have to do is put the whatever potential you want into the external functional and minimize. Now the difficulty with this process, the two difficulties are that it's a purely an existence proof. It's not constructive. We don't know the functional, and we don't know how to perform the minimization. Right? So for this reason, my sense is that when this appeared, it was regarded by almost everybody just sort of as a little curiosity. Because although it was a formal structure, one had no idea really what to do with it. Right? The thing which made the field take off was a paper the next year by Walter Kohn and Liu Shen. And what they did was two things. They told you how to actually carry out the minimization, and they gave you an approximation, which was uncontrolled in the sense of not being justified in any particular limit of some small parameter going to 0, but which seems empirically to be reasonably good. All right? So what they showed in this paper is that you can minimize the functional by constructing an auxiliary one-electron quantum mechanics problem involving non-interacting electrons moving in a potential which is determined by the density. Right? This is a potential which isn't known in the same way that the universal functional isn't known. Right? But nevertheless, they said if you solve this, you get the wave functions. You fill up the wave functions up to some Fermi level. That gives you the density, and also the sum of the eigenenergies gives you the energy. So that if you were to know this potential exactly, then the solution of this auxiliary problem gives you the ground state density and energy. All right? And the wave functions here in principle have no meaning except as moving parts in the machine, which is designed to give you the ground state density and energy. All right, so I already just said what was in here. The second part of this So one part, they gave you a procedure for carrying out the minimization in terms of solving an auxiliary problem. The second thing they gave you was an uncontrolled but apparently decent approximation for, this was supposed to be XC, for the exchange correlation potential, which goes into this. Right? The approximation they proposed was the so-called local density approximation, which is basically to bootstrap results from the uniform electron gas. Right? If you're talking about the case where the external potential is zero, you know the density is uniform, it doesn't have any space dependence, so the energy must therefore be a function only of a single scalar variable, the density. Right? So you can get that to various approximations by various numerical methods. And then you take this potential and you replace this functional of the density by whatever you would get from the electron gas at the density corresponding to the position that you're interested in. All right. So this started an enormous field. People did two things, essentially. First, worked on improved ways to actually carry out the solution to this Schrodinger equation, which in the late 60s and early 70s was not a trivial thing to do in the realistic cases one is interested. And second, they produced a whole bunch of variants on this approximation. In other words, a whole bunch of other approximations to this exchange correlation potential. Right? This is, of course, an enormous subject in itself. And I'm not really qualified to go into it. I'm just going to say two or three things. First, all the approximations here are, as I said, uncontrolled. They're essentially tested by comparison to each other, to exact numerics in a few cases, and to experiments. But they work reasonably well, so that the procedure now is a working machine which is very useful to wide ranges of chemists and material scientists. Right? The second point is that the essential computational task is to solve a single particle Schrodinger equation in some potential which has to be self-consistently determined. So what you do in practice is you take a starting guess for your density, that gives you a starting guess for your potential, you solve the Schrodinger equation, you get some wave functions, from that you construct a new density, you put it back in that, you solve the equation again, and you keep doing that until things stop changing. Right? And that naive self-consistent procedure works. Okay. So, the resulting intellectual construct, density functional band theory, is believed to be good for a wide variety of things. And of course, again, there's a whole field worrying about exactly how good it is, but it's reasonably good for total energies of solids, for crystal structures, which come by minimizing the total energy. So you can just solve the problem for different arrangements of the atoms and see which one is lowest, and that gives you a prediction for the crystal structure. Similarly, phonon frequencies, because atoms move very slowly compared to electrons. So essentially, you can get the restoring force exerted by electrons on a lattice distortion by doing a static calculation. Right? However, it's not so good for electron dynamics, for thermodynamics, phase transitions, and a lot of the interesting physics of correlated electron materials. Right? And so I wanted to make a brief discussion of why it doesn't work. Or let's say, what are the limits? Yeah?
You say, in its simplest form, how is it different from doing like self-consistent Hartree-Fock or self-consistent Hartree calculation?
Well, there are two differences, but conceptually it is a Hartree-like approximation. It is a electrons moving in a self-consistent field approximation. The difference is that the self-consistent field is obtained in a way which is both more ad hoc than Hartree-Fock, and clearly includes, in most cases, more of the correct physics. So it is conceptually very akin to a Hartree-Fock approximation.
You're doing a much better job for uniform density.
Well, let me take a step back. In fact, the way I would say it is that, by and large, not just uniform density, I would say that you're doing a much better job on the effective potential. So it is just like Hartree-Fock, a theory of electrons self-consistent, moving in a potential which is self-consistently determined by the interactions. Hartree-Fock is a relatively naive, if you like, first-order estimate of the effective potential determined by the electron wave functions that you have, all right? So the density functional theory business has a much better estimate of that effective potential, but one which is to a large degree phenomenological. Right? That's really the essence of it. Otherwise, it's conceptually not different from Hartree-Fock.
But that form is, who gives you that form? That's outside of the theory.
Correct. Well, again, so what we know is that there exists in principle an exact potential, which we don't know what it is in practice. Right? So then, as I say, these various approximations, the local density approximation is assuming that the things are not that far locally from a uniform electron gas, if you like, that the gradients are small. Right? However, nobody has ever been able to come up with a systematic and satisfying expansion in powers of gradients about anything. So in that sense, it's phenomenological. And indeed, in many ways, especially in the quantum chemistry literature, where this is a world where this is used extensively, the whole thing has the flavor of Ptolemaic astronomy. It really, one takes a theory which has no particular rational basis, all right? Like Ptolemy said, you view planets as going in circles around the Earth. And then to fix up differences with experiments, you put on little epicycles. And these are the modifications. So the original Ptolemaic picture is like local density approximation. And then the epicycles are things like GGA, this V3 lip thing, which is actually making a functional, which is a combination of some small fraction Hartree-Fock and some small part local density approximation. And so you put more epicycles and you get better and better agreement with your universe of data. Right? So it's intellectually unsatisfying in some sense. But you have to remember that for many years, Ptolemaic astronomy was actually useful to many people for many purposes. And in the same way, this is useful. Up to a point. Right? So, there are a number of reasons why it's not completely useful. But one of the more subtle ones, which was pointed out to me by Copliar, was that, just fundamentally speaking, this theory is built on optimizing a functional of the particle density. And for many problems, density is not the variable that you want to look at. Right? So even if there is, in principle, an exact functional of the density, whose minimization would distinguish various things, if phases with almost completely different properties, in fact, have the same, almost the same density, then a theory built on density differences would have to work extremely hard to capture those differences. Right? So in other words, the variations we're interested in correspond to very small variations in density, so you don't want to look at them as functionals of the density. Right? Here is an example from the world of correlated material science. This is a family of compounds, calcium, strontium, ruthenium, O4. Basically, changing calcium and strontium changes bond angles by a small amount, it changes bandwidth by a small amount, but doesn't change the basic electron concentration. Right? This is a phase diagram in the plane of temperature on logarithmic scale and ratio of calcium to strontium. The first thing I want you to notice just is that this phase diagram has lots of different colors. Right? That means that the material exhibits many different phases, depending on exactly what you do. Right? Among the phases are a Fermi liquid phase, at low temperature in some range of strontium concentration, and unconventional superconductor believed to be spin triplet at the strontium end member part, a ferromagnetic metal, an antiferromagnetic insulator, an antiferromagnetic metal, and so on. All right. All of these phases have densities which are extremely similar. Right? So a theory which is built on, although the general formalism of density functional theory says that each of these phases will correspond to a different density, because the density differences are so small, it's much harder work than is necessary to try to distinguish these phases by their differences in density. You want a theory which is built on a better variable. Okay. The other thing is that, of course, the ground state is not the only interest. This density functional thing that I explained to you is really a ground state theory, and the attempts to make it work for excited states and thermodynamics are very awkward and run into considerable difficulty. All right? So, in fact, there are different phases at different temperatures, and you need a theory which accounts for those, and in particular accounts for, let's say, entropic effects. So for example, if you come down here at calcium 1.4, strontium 0.6, that's about here, all right? As you come down in temperature, this white phase, which is paramagnetic metal, or this edge here, which is correlated metal, if you measure the magnetic susceptibility, what you see is that it's a rapidly rising function of lowering temperature. So it just looks naively like there's a susceptibility which is approximately 1 over temperature. In other words, that there's local magnetic moments floating around. And indeed, approximately 1 local spin-half moment per unit cell. Right? So these local moments go away either into a ferromagnetic metal, or if you're slightly on this side, into a paramagnetic metal. But they're here, and you want a theory which knows how to capture that physics. All right? To continue, not just thermodynamics, but also dynamics and excitation spectra are of interest. All right? Here is a measurement of photoemission, which is basically the probability of removing an electron at a given binding energy for a series of materials, strontium vanadate, which I mentioned before, lanthanum titanate, yttrium titanate. So these dots are photoemission spectra obtained by Fujimori a number of years ago. You see they're characterized by here a little peak at the chemical potential and a big sideband. And then as you go down this series, the little peak gets littler and then goes away completely. Right? So that's excitation spectrum. If you just take the band theory calculations of these materials, which are supposed to reproduce their energy and so on, you get predictions which are completely wrong. In particular, you get a big peak here at the Fermi level and no sideband. So even if you had a theory which you could implement exactly, which got the energy right, there's no guarantee that the wave functions have any meaning, and you need, therefore, to get excitation spectra. Okay, so this is to summarize what I told you so far. Quantities of interest are obtained from the solution of an auxiliary problem plus a self-consistency condition. And I think that that is an important approach, which I'm going to come back to a bit later. It's built on an uncontrolled, but in practice very useful approximation. And it has clear difficulties with excitation spectrum, higher temperature behavior, phase transitions to other ground states. And it focuses on the density, which is not necessarily the variable you want. Yes?
So let's say you one day manage to find some exchange correlation potential for material that seems to work.
Yeah.
Is there anything what can we learn from that specific choice that works about the phenomenon of material we're studying? In other words, if you pick correlation potential A over B, does that tell us anything, or is it just, I don't know.
Okay, so I mean, I guess I personally have never been very sympathetic to that point of view. So my answer to this is basically the Ptolemaic astronomy example. I mean, the question was essentially, as you improve your exchange correlation potentials to get better and better descriptions of a class of materials, what does it tell you? All right? And in my view, not much more than adding epicycles to Ptolemy's original structure tells you. Right? From a principal point of view. Now, as we'll see, in practice, these things do provide, even though the wave functions have no meaning, and in some cases give you information about excitation spectra which go very badly wrong, right? There's still a lot of things they tell you about materials which seem to be quite reasonable and correspond to experiments. So there is a whole industry, as I say, especially in quantum chemistry, where there's enormous sums of money at stake in actually getting good energetics, basically, so you can find out which little bit of one drug matches well with which little bit of one receptor. Right? They really want to get this right. Right? So there is a non-trivial question: as you improve your description of energetics, how well does it work for describing other things, like what happens as you move atoms apart and break chemical bonds? Or therefore, what are the orbitals which really lie very nearby in energy, and what is their shape? Things like that. Right? And there is a hope that as you improve the density functionals to get better energies and so on, that you will get more accurate information about that kind of thing. But to my mind, it's some kind of miracle that the whole structure works as well as it does. Okay. Now, so that was one set of background ideas I wanted to present in this lecture. Now I want to change gears, having said to you that excitation spectra are important and interesting. I wanted to review a theory which is of actually slightly more antiquity than density functional theory, which is basically describes the language of how we think about excitation spectra, and that is Fermi liquid theory, which really goes back to both Landau and Rudolf Peierls. So just to start the discussion, consider free, meaning that there's no potential, fermions interacting with a short-range interaction. What that means in practice is helium-3. Right? So if you neglect interactions, you have a Hamiltonian, which is just the kinetic energy. We know that the wave functions that you get are just Slater determinants of plane waves. Right? And we know that the physical content of this theory is what I've sketched here. In the ground state, you just fill up however many k states as you have particles. That gives you a filled Fermi C, which I sketched here. This box is just to enclose some random two-dimensional sheet of k space. In the excited states, you could think of as particle-hole pairs. So I take an electron out of the Fermi C, leaving behind a hole which is red, and I put it somewhere else. So here's an example of an excited state with 3 particle-hole pairs. I can label wave functions by excitations above the excited states. Right? Now, if I have non-interacting fermions, then the energy of then the excited states are particles and holes, but because they don't interact, these particles and holes aren't correlated. I can just look at one of them. And the particle or hole has an energy which is basically its linear distance from the Fermi surface. All right, so it's basically something which has dimensions of velocity times k measured from the Fermi surface. All right? Now, as we all remember, I hope, from elementary statistical physics and condensed matter courses, the fact that you have a big Fermi surface means that you have a large density of low-lying excitations. And the result is that at low temperature, both susceptibilities, which polarize these particle-hole pairs, and specific heat, which basically counts the number of electrons, are large. In particular, the specific heat divided by temperature is constant at low temperature, and is proportional to the particle mass. Right? So that's non-interacting electrons. Right? And I said that things propagate freely. Now, when you turn on interaction, 2 things happen. First, the energy of an excited particle depends on how many other particles are excited. And second, a state of a given number of particles and holes is not an exact eigenstate. A particle can, for example, decay into a particle plus a particle-hole pair. So here I tried to sketch a decay process in which this particle here decays, so it moves closer to the Fermi surface. That's this guy. And it produces another particle, this guy, and another hole, that guy. Right. Now you'll notice something you could already see from this picture, which is the basis of Landau and Peierls thinking, is that as a particle approaches the Fermi surface, its phase space for decay decreases. Basically, here I'm going to show you this just by going back to my little example and hiding all the other particles. So if we focus on this guy, the energetics of the decay are you start out with an initial energy, which is how far this guy is from the Fermi surface. You wind up with a final state. Here I guess I made a different decay process. So this guy moved closer, you made a particle and a hole. And all these guys have to fit closer to the Fermi surface than my initial state so that energy is conserved. Right? If you work out the kinematics of that, you will discover that the phase space for decay is proportional basically to the energy relative to the Fermi surface squared. So the decay probability goes down as particles get to be closer to the Fermi surface. All right, so as you go to lower energies, decay processes become negligible. However, the modification of the energetics of a particle by the other excited particles is not negligible. Right? So based on these 2 ideas, first Landau and Peierls, and then a variety of other people, provided an increasingly sophisticated set of formal arguments, which said that these statements were true to all orders in perturbation theory, right? And explored their consequences. The result is what's now called Fermi liquid theory. These are the references that I like, which are in your notes. right? And the result is that in many circumstances, the low energy properties of a system of interacting fermions are those of non-interacting systems, but with renormalized parameters. All right? Now, what I would like to do now is formalize that statement a little bit. All right, and also define a concept that I'm going to want later. Okay, so let me consider the electron Green's function. Suppose I take my many-body system, and I just take, and I consider a system with some number of particles n plus 1, and I have a bunch of exact eigenstates of some momentum. All right? So I'm going to measure the energy of this with respect to the ground state energy of the n particle system. So when I write Em of k, it's the energy of this guy measured relative to the energy of that guy. Right? Now, with this I can then define the electron Green's function, which is basically the Fourier transform of the time-ordered product of the creation operator of an electron in the state of momentum k at time 0 and then annihilating it at a different time. And this k is a time-ordered symbol. So this guy creates an electron in the state with wave function proportional to e to the ik dot r. All right. Now, we know, and stop me if this is something that you want me to amplify. This Green's function obeys a spectral representation, which I can write like this. Right? So that this Green's function, which is a complex function of frequency, is determined by this quantity A, the so-called spectral function, which, if you just play the usual analytical games with this, is the imaginary part of the Green's function. Right? If you work out what the imaginary part of the Green's function is, it's this nice, slightly lengthy formula written here, which boils down to saying that the spectral function measures the overlap of the exact eigenstate of the n plus 1 particle system with the states created by psi dagger or created by psi, or the exact eigenstates of the n minus 1 particle system with the states created by psi. Right? So that's the information which is in this thing. Right? And I should also say, of course, that while the distinction between n and n plus 1 particles is crucial if you're talking about chemistry and small finite systems and condensed matter systems, if you're dealing with an essentially infinite number of particles, then the difference between n plus 1 and n is not important. Okay. Now, if you were to have a non-interacting system, then of course this would create an exact eigenstate because just the one particle states are the exact eigenstates. So it creates an exact eigenstate which I'm going to call M1. So that means when I act with this guy on the ground state, I get precisely the exact eigenstate of the n plus 1 particle system with this momentum, and I just get exactly 1. That means, if you go back to this formula, that the spectral function is just a delta function at the energy of this state. Because after all, there's exactly one state that you create. Now, if I have a general interacting system with no particular properties, then the state created by the non-interacting particle, psi k, doesn't resemble any eigenstate. It has a large overlap with all of them. So when I compute this thing, I just get some function, which is presumably a smooth function and has no structure whatsoever. So then instead of being a delta function, the spectral function would be smooth. All right. So the statement of Fermi liquid theory is that as the wave vector goes to the Fermi surface, the state created by this creation operator tends towards having a non-zero overlap with one unique state, as well as some overlap with the continuum of others. So if I go back to this matrix element question, what I see is that as this k goes to the Fermi surface, this approaches a coefficient, conventionally called z, times a delta function which picks out one particular exact eigenstate, plus a smooth part. In other words, the spectral function tends to a delta function, called in the jargon of the field the quasi-particle peak, plus a smooth or incoherent background. And this thing z here is an important concept called the quasi-particle wave. So there's a nice picture here from RevMod Phys on photo emission, which shows this. If you have a non-interacting system, basically what you see in your spectrum is a series of delta functions. As you change k, you get delta functions at different energies. That's because your creation operator creates an exact eigenstate. In a Fermi liquid, if you're far from the Fermi surface, you see a broad structure. As you go close to the Fermi surface, you grow a sharp peak of some small but non-zero weight, which coexists with the broad structure. Right? So that's the picture one imagines from Fermi liquid theory. This quantity Z is the relative weight of the near Fermi surface peak. And you can define a dispersion of this near Fermi surface peak by saying that over the range of Ks where the peak exists as a reasonably well-defined excitation, you can follow its position as a function of energy. That gives you a dispersion, which will be different from the non-interacting fermion dispersion. Okay, so finally, there's an alternative mathematical formulation of all this, which involves the electron self-energy. I can write the Green's function relative to some reference non-interacting system in this way. So the Green's function is omega minus Ek, which is what I would get if I had no interactions, minus the self-energy, which is just a mathematical expression of the difference between the true function and the one given by the non-interacting theory, right? So the self-energy has real and imaginary parts, so if I entangle this into the imaginary part of the Green's function, what I see is a formula like this. And basically the real part of the self-energy, so you can see that if the imaginary part is small, as would happen if K goes to the Fermi surface and frequency goes to 0, then this becomes more and more sharply peaked about something which satisfies the equation omega minus Ek minus real part of sigma equals 0. So this real part gives renormalization of the dispersion of the peak and overlap with the exact eigenstate. The imaginary part represents the decay. Right? Again, in a Fermi liquid, this imaginary part goes to 0 as frequency goes to 0 and K goes to Kf. And the velocity is related to various objects of the, is related basically both to the, so then the overlap between this and an exact eigenstate is given by this thing Z, which is related to the frequency derivative of the self-energy. And the velocity is given by the frequency dependence of the self-energy and its momentum dependence. So this is just a mathematical reparameterization of all the things I just told you. All right? And basically, in subsequent lectures, I'm going to want these things, so I just thought I should mention. All right. So to summarize, Fermi liquid theory is basically an arrangement of many-body physics which allows one to focus on the coherent, that is to say, quasi-particle peak part of the Green's function, with the effect of the incoherent parts in all the interactions being subsumed essentially into renormalizations of the particle velocity and things of that nature. All right. So this is a series of ideas. All right. Oh, I'm sorry. So before I go to how well this works, I wanted to give a slightly different perspective on all of this, which introduces another concept which is important. Right? Let me just pose to you for the moment the Anderson impurity model, which is probably conceptually the sorry. Yes.
So you're not really, this Fermi liquid theory, I'm a little confused about whether you're treating the interaction as a perturbation or whether this holds for this Fermi liquid theory. I mean, because you're using the self-energy, you could say, okay, I just perturb around the free fermions.
Correct. Well, so there's several different statements here, but the loose way of saying it is that Fermi liquid, and this is really the way that Landau and Peierls originally thought of it, was that what Fermi liquid theory is a bootstrapping of results which you can see to second order in perturbation theory to all orders of perturbation theory. So it's really a statement that the qualitative features that you see to second order, all right, remain correct just with changes of numerical values if you carry the perturbation theory to all orders and make an exact statement. Okay, now, there's a different point of view which is discussed in the Revlon Phys article by Shankar and was discussed earlier in the context actually of properties of models like this by Nociera. You can think of this at Fermi liquid theory as an effective field theory which represents the low energy limit of an interacting Fermi theory. Right? And there's a renormalization argument you can cook up, which says essentially the same thing. Or you can then detach it from its perturbation theory to all orders and just say it's an example of, it is one example of the kinds of stable low energy fixed points that you can get in fermion systems. right? So, but for loose purposes, just think of it as second order perturbation theory bootstrapped to all orders. And of course, it may or may not work. It may break down either because it is a statement about the low energy limit of things. It will clearly break down as temperature goes up, as excitation energy goes up, or the ground state could be different. You could have a phase transition into a different kind of state. So, and I guess, I mean, really the right way to say it is that it is a, let's say, general and consistent description of a particular low energy fixed point of interacting Fermi systems. And you're best off avoiding the question of how it actually got there, in common with most discussions of low energy fixed points. Right. But you can show basically that it is a stable fixed point with a spectrum of marginal operators, which are the knockout parameters. Okay, now, for a slightly different perspective, let me go back to this model, which, as I said, is in some sense the simplest many-body model. It's one of a large number of models in condensed matter physics which have the name Anderson attached to them. In this case, what we do is we take a model of one localized level with some interaction, coupled to some number, which we will normally think about as being a continuum of other levels. All right? So here we have a level that can hold 0, 1, or 2 electrons. There's an interaction term which disfavors having 2. There's a hybridization which lets an electron hop off of the local level into some other band of electrons, which have some dispersion but no interactions. Right? So this is interactions just at one point, coupled to a non-interacting continuum. It's still an interacting model. If you like, it's a 0 plus 1 dimensional quantum field theory. You can integrate out these guys, but there's still an interaction here, which doesn't commute with this term. All right? This wants to constrain the occupancy, this wants to change the occupancy. Right? However, it is a simple enough kind of 0 plus 1 dimensional model that perturbation theory in U actually converges. Okay, now, if U equals 0, this is just a simple solvable hybridization problem. And we all know how hybridization works. If I throw away this U, I just have a localized level hybridized to a continuum. You can describe that by a Green's function for the d electrons, which has a general form that I wrote here. This is just for the non-interacting model. When you know the answer, what you get is a more or less Lorentzian scattering resonance, which I sketched here. So the density of states, which is the imaginary part of the Green's function, is peaked at some energy. And the key parameter in this thing, Green's function, you have your frequency, you have your bare energy level, and you have this thing which I wrote as delta, which is known in the jargon of the field as the hybridization constant. Right? And this expresses the effect of coupling to the leads. Right? If you work out what it is, because this is a trivially solvable model, what you see is it's a sum over all the lead states, an amplitude to hop onto the lead squared, and then basically a lead density of states. That's the imaginary part, and then this is its Kroner-Kronig transform. So the real part of this thing basically says how is this peak shifted from the bare energy due to coupling to the continuum. The imaginary part, which gives a width, says how long does an electron remain on this level before it hops away into the continuum, or how long does the level remain empty before an electron hops in to fill it. All right? So far, it's so simple. All right? And if I want to discuss, so if I'm really talking about a resonance in a Fermi system, there's a chemical potential, and I just fill the resonance up to the chemical potential. All right. Now, there is something which you can demonstrate directly, just from the non-interacting model, and which Langworth and others showed holds more generally, which is called the Friedel sum rule, which in this language basically says that the total number of electrons is related to the ratio of the real and imaginary parts of this guy at the chemical potential. All right. Now let's take the other limit. Instead of taking U equals 0, let me turn off the hybridization and consider the isolated atom. Right? In that case, the occupation number is conserved, so I just have eigenstates, which are simple enough that even I can find them. There's an eigenstate with 0 particles, 2 eigenstates with 1 particle, and an eigenstate with 2 particles. All right? Which ones are occupied depends on the chemical potential. If the level is less than the chemical potential, or the chemical potential is bigger than normal, then I want to put at least 1 electron on it. All right? However, the cost of putting 2 electrons is twice this, plus my correlation energy U. If that guy comes out to be bigger than the chemical potential, then I want to put 1 and not 2. Right? So there's a range of parameters where the ground state has 1 electron and is twofold degenerate. Now let me contemplate the photoemission spectrum of this situation. Well, for negative energies, I can remove an electron because it's singly occupied. That gives me a sharp peak at the removal of energy. I can add an electron. If I add an electron, I have to pay the correlation cost. That gives me an addition peak, which is somewhere, let's say, above the chemical potential, if the chemical potential is in this magic regime. So the imaginary part of the Green's function, which is the photoemission spectrum, is 2 sharp peaks. And there's something a little funny about this peak, because I have 1 electron, it has a definite spin. So if I really want to do this precisely in a canonical ensemble, I would say if the spin is up, for example, then if I try to remove an electron or spin up, I would get a peak here. If I try to remove an electron or spin down, I would get nothing. If I considered a grand canonical ensemble of these things, then basically I get a 50% chance. If I tried to remove a spin up electron, I would get a 50% chance of finding something, so this peak would have a weighted half. All right. If I turn on the potential, then this thing is not conserved. The states have to broaden, so you might expect you get a 2-peak structure. But recall the Friedel-Sum rule, which said that in a 0-dimensional system, there's no phase transition as a function of U, so the ratio of the imaginary to real parts of this thing at the chemical potential has to be consistent with the density. The result is that when you solve this model in the large U limit, at 0 temperature in the ground state, you not only get 2 broadened peaks here, but you get a central peak at the chemical potential, which provides the correct sum rule. So these are calculations actually produced by Sunny Wang, who is here for a somewhat different purpose, just displaying this fact. This is far from the first calculation to show this, but it just happens to be something I had. So this is the spectral function for the non-interacting model. You see a peak centered at 0. As you increase the interaction strength, you start to see side bands develop, but still a central peak. As you increase the interaction strength even more, the side bands move out, and the central peak remains. Right? And this central peak, as I said, is the thing which gives you, via the Friedel-Sum rule, the correct density. All right. So the low energy physics of this, at let's say the strong interaction limit, is described by the behavior of this central peak, which looks just like a renormalized scattering incidence. It has a different width than you would get in a non-interacting problem. Perhaps a slightly different shape, but it's basically a beast of the same ilk. Right? So you can discuss the low energy physics of this problem in terms of a local Fermi liquid theory. The weight of this central peak is precisely the quasi-particle renormalization Z that I defined before. Right? Now, it's amusing to ask, how would density functional band theory represent this solution? Right? Well, density functional band theory is some non-interacting problem with some sort of self-consistently determined potential. So all it can do is give you one single scattering resonance with properties which are fiddled to reproduce the correct energy and density. Right? So this is a more concrete example of how even if you had the exact density functional for this problem and got the correct energies, you would get the incorrect excitation spectrum.
This is
Yes.
reading it off the bands, is that,
What do you mean?
where are you getting the spectral function given the density?
Oh, this. No, I'm saying that for this simple problem, it can't do anything else than give you an effective one single Lorentzian resonance of some kind, because it is a non-interacting problem in a self-consistently determined potential. So there's nothing in the theory that can give you more than this. I'm not making a precise statement about the shape of this or the width, right? Those parameters would be cooked up to give you the correct ground state density and energy, assuming you had the correct density functional for this problem. But it would have to be something of this form.
But in principle, there's a functional that takes the density and gives you the true spectral function.
No, well, yes, but that's not what density functional theory does. Right?
Sure.
Right? So again, this is just a statement. Well, actually, in fact, I guess I agreed too rapidly. But let's go back. So density functional band theory produces a spectral function, right? Which is the cone sham eigenvalue for this problem, which you should view as nothing more than little cogs in a machine whose purpose is to produce you the energy. They don't necessarily have a physical meaning. And this argument is to show you that, in fact, the physical meaning that you would infer from this goes quite wrong because it doesn't have the sidebands. And it will, in fact, actually get the wrong width here as well.
I guess my statement was not that you should look at the conditional eigenvalues for this out, but there should exist some function that takes.
Well, so there is something, well, all right, so I would claim that if you make a functional of the density only by the procedure that I sketched overly rapidly here, all right, then you've lost too much information. So this functional of the density doesn't know enough to give you a spectral function. There is a different function, let's say of the spectral function, which will give you the spectral function, or a functional just of the fermionic wave functions that give you the spectral function. But by the time you've done all the integrating out to get you to this, you've lost the information which would enable you to compute the spectral function. Yes?
What's the simplest variational wave function for going out to some of these?
Well, actually, as you'll see, I don't like variational wave functions, so I don't have this at my fingertips. But so the question was, what's the simplest variational wave function? And in fact, this is a good opportunity to make a small digression, which I probably should have put in my notes, but didn't. And don't worry, I'll get back to your variational wave function in a second. So, let's go back to this picture for a moment. Suppose we're in the strong correlation limit, and we forget about hybridization, right? And the chemical potential and the interaction energies are fiddled so that we have this situation, right? The ground state has one electron of some definite state, right? Now, if you turn on a weak hybridization, I said rather glibly, well, it broadens this. But if you think about it, basically, what's really going to happen is you start with, let's say, a spin-off. The fact that you couple to a broad band of conduction electrons means that an electron can hop off. That gives you the zero particle state, which is much higher in energy by this amount. So then that state is almost immediately filled by another electron hopping back from the conduction band. Right? So that means that the processes, if you do second order perturbation theory around this, are basically ones that take your spin that you start with and reverse its direction. Right? So they allow this, which is a local moment, to exchange itself with the conduction band. So the model which correctly represents the low energy physics of this situation is the so-called Kondo model, where you say your states are spin up and down, coupled by an exchange term, two conduction electrons. Right? And so now, in a moment, I will come back to what is a variational wave function for this model, which starts to do these things. But if you just think about this model to start with, then this behavior is sort of remarkable, right? Because what it says is that you start with a spin, and then if I look at the low energy physics is of a hybridization resonance. So the low energy physics of a model which starts with a spin coupled to conduction electrons, if the coupling is anti-ferromagnetic, produces something which looks like not a spin, but an actual charge degree of freedom that can hybridize with the conduction electrons. Right? Now, from one point of view, this is all sort of trivial. You might say, well, this spin really came from a model of real electrons, and Fermi liquid arguments or analyticity of perturbation theory in U tells me that the low energy physics should still be Fermi liquid like. This is just some sort of intermediate energy artifact which I can forget about. Right? However, it is in fact correct, or at least believed by everybody to be correct, that if I really start from this model, for example, if I imagine taking this to be a spin-half nuclear spin of some nucleus, exchange coupled to a Fermi sea of electrons, and I were really able to obtain the low energy physics, which would be micro, 10 to the minus 20 Kelvin or something, I would see a scattering resonance like this. So the low energy physics of this model turns itself into a hybridization. All right, now, that said, the variational wave functions that take this into a low energy spectral function like that were introduced in the condensed matter physics context by Varma and Yaphet. And what they boil down to is bound states of spins and conduction electrons. Right? So that you consider spin up, sum appropriate sum over k, c negative k down, plus corrections. And I can fish out the reference for you a little later if you want it. Right? But if you play games with this kind of wave function, you reproduce that kind of low energy physics. And I don't know off the top of my head how to make a wave function that starts directly from the Anderson model and does that. But presumably once you see this in the spin language, it shouldn't be too hard
That's
to cook up.
Schönhammer.
Ah, okay.
It's in this.
Oh.
You can read about it in Mayhem's book. It's very nicely designed.
Okay.
It's just superposition of one electron, singly occupied. It's actually, I think, more transparent.
Okay. All right, so Schönhammer and Mayhem's book. But it comes down to superpositions of different occupancies of the local level with different configurations of the different excitations of the conduction bands. Okay, so part of the reason that I took you over this long digression, both through density functional theory and through this, is that where I'm really going with these lectures is that the Anderson impurity model and its obvious generalizations are the auxiliary problem whose solution gives you insights beyond, let's say, density functional theory into many-body electronic structure of materials. All right. So that is, in fact, all I wanted to say on this. I will ask for questions, and then I will start in, if we have a few minutes and people aren't starving for lunch, I will go on to lecture number 2, which you don't have time for. All right, so, yeah.
The statement that there's no phase transition is a function of dependent on density of states, right?
No.
What if you had like a pseudo-gap density of states for the Anderson model?
Yeah, within perturbation theory is even better. Basically, you would get into trouble if you had a density of states with a big enough divergence, I believe. So the statement is that there's no phase transition with densities of states which are constant and less in this model as a function of U. Now, you can decorate the model, as Sunny here knows, in various ways which will give you a phase transition. All right, but that's a subject for another talk. But generically, in low dimensions, you have more fluctuations and it's harder to get phase transitions. Now, I think that what you were thinking of is that, in fact, it goes the other way. That, actually, so maybe I spoke too fast. Let me think about this offline and get back to you, because it's certainly true that this class of models, if you suppress the density of states, gives you phase transitions as a function of this J. So I guess I would have to think a little bit about what happens if you go back to the Anderson model. I guess it's conceivable. Yeah, so let me think about that. That's an interesting question. All right. So other questions?
There are 2 questions online. The first one is, what is strong correlation exactly, and why DFT theory fails to describe these systems?
Okay. All right, well, actually, that will sort of come here, but let me just So the why DFT theory gets you into trouble was really what I tried to address in a rather qualitative way by these figures. I don't know if they're visible to the online person, but there are three things. First, even if in principle a density functional calculation would let you describe this evolution of phases, we don't have density functionals that will do that, and part of the reason is that the actual density differences are so small that you would need a nauseatingly refined treatment to make the density reveal this to you. And even more conceptually, it's not at all obvious that it's sensible, even though it is of course true, to use the density as a variable which lets you distinguish between a paramagnetic metal and a ferromagnetic metal. They do have slightly different densities, right? But density is clearly not the right variable in which to frame this discussion. All right? The second point is that it doesn't tell you about local moment physics, which I sketched here. This sort of divergence of the susceptibility shows that there are essentially of order one local moment per unit cell. And I don't know of a density functional description that will do that and give you a Fermi liquid ground state at low temperatures. And finally here, if you do density functional band theory, you can see that it completely mispredicts the experimental photoemission spectrum. So broadly speaking, strongly correlated materials are those for which density functional theory fails for this variety of reasons. Right, so was there a second question?
Yeah, the second one is, can DFT be adapted to a system with ground state degeneracy?
Ah, right. So basically, I'm out of my depth here. The short answer is yes, but there is a very long answer, which gets rather complicated. And everything I've seen is sort of what I said to Patrick before, that really what you do is you make a system without ground state degeneracy by breaking slightly and artificially the symmetry that gave you a ground state degeneracy. Right? And then you can investigate your density functional properties, including energies and things like that, as a function of how this parameter goes to zero, or you know, the orientations of this symmetry breaking field. But everything I've seen, you put in an explicit symmetry breaking, and then you argue about what happens as it becomes small. So it's essentially using results for systems that don't have a ground state degeneracy to say something about one that does. All right, are there other questions? All right, so look at what I will just say very briefly here, because it is getting close to lunchtime. I wanted to give a little bit of what you might call a botany of correlated fermion physics, just to try to put some experimental flesh on these relatively general concepts. Right? And I wanted to start with helium-3, which is the canonical example of a Fermi liquid.
Can we get the lights off again?
Oh, yes. It's true, especially that's not the world's most good phase diagram. Okay. So you take a bunch of helium-3 atoms and you put them in a box at some pressure, and you get the phase diagram, which is sketched here. Right? So helium-3 is the canonical example of fermions with a short-range interaction. Right? At very high temperatures, what you get is a gas. You have a liquid-gas crossover, which is typically not a phase transition, although there's a little hint of a first-order phase transition at sufficiently low pressures. As you lower the temperature, what you get is you go from gas to liquid. This becomes a quantum liquid. And then at very low temperatures, it's unstable, or at high pressures, it's unstable either to a superfluid phase or to a solid phase. Right? So the generic statement that you should take away from this, at low temperatures you have a quantum liquid phase which is unstable to phases with interesting properties, either localized solid phase or, more interesting, exotic superfluid phases. All right. Now let's look in a little more detail at the properties of this normal phase. Right? I'm showing here results from a paper of Dennis Graywall in 1983, which is sort of the capstone of many years of people's investigations. So shown here is the specific heat, plotted versus temperature on a low temperature scale. All right? What you see, the black line, two black lines are data at two different volumes, therefore two different pressures. Higher volume is lower pressure. what you see, this is not the best scale for displaying this, but it shows so many other things I wanted to show it, is that at low temperatures, the specific heat is linear in temperature. The slope is a bit different. The zero pressure, higher volume curve is a little less steep than the higher pressure, smaller molar volume curve here. All right? So these guys are linear in temperature at low temperatures. If you fit them to free fermion, well, I should say these two dashed curves are what you would get if you just forgot about interactions and you take what we know about the helium mass, the helium density, which comes from the smaller volume, and you just do free Fermi statistics. So you see it's quite different from the experimental curves. These two dashed curves are what you get if you just force a fit to the slope. So you say, all right, I have free fermions just with a different mass. This dashed curve is the one which fits the lower pressure. You get a mass of almost 3 times the mass of helium-3. This curve is the one which fits the higher pressure. You have a mass of 5 times the helium-3 mass. All right? So low temperature behavior is what you expect of free fermions, just with a mass which is both increased by interactions and is dependent on pressure and other parameters. All right. Next interesting thing about these curves, if you look at the actual data as compared to these things are just predictions of this is just free Fermi statistics, you'll notice that these curves exhibit a saturation regime, particularly pronounced at higher temperature. So you have a quite low scale at which Fermi liquid theory is obeyed, lower than you would infer from free fermion theory, and an intermediate range with an approximately constant specific heat. Right. You can also look at other quantities. In particular, the charge susceptibility, which is typically parameterized as a compressibility kappa. That's this curve here. You can plot the charge susceptibility normalized to its non-interacting value. Right? You see it has a strong pressure dependence, and the charge susceptibility is strongly suppressed. Right? This number is 0.01, 0.05, 0.06. Right? This is the specific heat coefficient curve. And you can also plot the spin susceptibility. The spin susceptibility, just for more or less historical reasons, is parameterized by a so-called Landau parameter. So that the measured spin susceptibility is related to what you would get if you had non-interacting particles with the renormalized mass. So just renormalizing the mass doesn't give you the correct spin susceptibility. You need to correct things by a further factor, which is this 1 plus F0s, which is plotted here, and is clearly not zero and is relatively weakly pressure dependent. So all of these things are to say that essentially all of the low temperature properties are those of non-interacting fermions, but with substantially renormalized parameters. And this is probably the best evidence that Fermi liquid theory really works. Now you will notice that while Fermi liquid theory, which is let's say, description of a particular stable low energy fixed point, tells you what kinds of renormalizations to expect, it's silent on the values of all of these things. If you want a theory for what the value should be and how it should depend on pressure, you need something else. All right. Now, you see here that the specific heat flattens off. It's sort of interesting. This is one at higher molar volume. He didn't have one at the lower molar volume where you have a wider saturation regime. But basically, you see the point where this guy flattens here is around 0.4, which is about the place where the entropy, which is the integral of the specific heat curve, reaches a value, reaches a very interesting value, which is log 2 per particle. Right? So in a sense, what this is telling you is that in this regime, you have something like a free spin for each particle. Right? In other words, the statement that the entropy is log 2 per particle is very naturally interpreted as saying that the spins of the particles, which are nicely organized in the Fermi liquid ground state, have become essentially completely decorrelated. So what you have are free spins plus the positional entropy of the liquid. Right? So there's a qualitative idea you should take away from this, which is that the motion of particles forming the low temperature, more or less coherent fermionic state, quenches the entropy of the spins. Right? And that the motion of particles is sufficiently blocked by the fermion-fermion interaction, that it doesn't take much going up in temperature before the particle motion is decorrelated enough that it cannot organize the spins, giving you thus free spin behavior. A sensible description of this regime is again beyond the scope of Fermi liquid theory. All right? Finally, as you saw from the phase diagram, there are interesting transitions to other states. And while I don't want to review this, people have obtained some ideas about which states might be favored and rough orders of magnitude of transition temperatures. A detailed theory or a detailed understanding of these phase transitions, which states you get, what is the value of the transition temperature, how does this move with pressure, and so on, is really beyond the scope of Fermi liquid theory. All right, so I think that's probably a good place to stop at this point, and then I will pick up next time with application of these ideas to correlated materials. So is there questions about this? I see, the only question is when we can have lunch. All right, so we'll stop.